Today's video will explain how to design a large inheritance tree using shapes as an example. Hello, I'm James Helfrich. Large inheritance trees can become unwieldy, especially in the face of changing needs and requirements of the client. One of the main techniques we have to avoid this is to give each level a semantic meaning. This video will demonstrate that process by designing a large inheritance tree around shapes or drawn objects. There's a few best practices when working with large inheritance trees. The first is every base class should map to a design concern. Alignment is the measure of how well a class design matches a design concern. Good alignment makes it more likely that changing requirements will not result in changing the structure of the design. Do not worry about balancing an inheritance tree. Whenever we optimize on the wrong variable, it is likely we will fail to make optimizations on the right variables. Since a balanced tree offers no advantage over a non-balanced tree, do not worry about balancing. Each level in an inheritance hierarchy should mean something. As a level of an inheritance hierarchy is identified, take the time to describe it completely and accurately. Difficulty in producing a good descriptions are indications of poor alignment. Unambiguously communicate the meaning of each division in an inheritance tree. Each member of the development team who makes changes to the inheritance tree should understand the philosophy of the design. Communicate that both in the code base, through comments, and through other mediums. Choose base class names carefully. Use intent-revealing names. One should be able to determine the purpose of a class or function or variable or anything really from the name alone. Let's take a look at an example. A drawing program needs to represent many types of shapes: points, lines, circles, rectangles, parallelograms, arrows, curves, ellipses, cubes, spheres, etc. The total number of shapes is unknown at the onset, but there'll probably be several dozen when the application is finished. So how are we going to solve this problem? Well, first of all, I'm going to have the base class, and every shape derives off of this. And then I'm going to have the dimensions, how many dimensions I'm going to have in this shape. Next, I'm going to have the complexity. In other words, how much information is required to represent this particular shape. And then finally, I have the individual shape itself. Then this is the concrete derived class. Okay, so now I have the levels. I have the strategy and the definition for each one of these. Now and only now will I go about the process of defining the classes themselves. So I'm going to start with my shape, and this is my base class. And they're going to have a one-dimensional shape, but I'm also going to have a two and a three-dimensional shape as well. And all these are going to derive off of shape. Now let's drill down on the two-dimensional one for a minute here. And I'm going to have a complex shape, but I might also have a simple and a compound shape. And what's a complex shape? It's going to consist of many different control points, where a simple one will just be, for an example, a regular shape like a circle or triangle. And a compound will be a shape that consists of shapes. And all these are different types of two dimensions. And finally, let's define some concrete classes. I'll have a square, but I'll also have a circle and triangle, and all these are different types of simple shapes. When I'm finished here, I have not only my inheritance tree, but I also have a strategy. So when I want to add something new, for an example, a cone, or if I want to add a line or an arrow, then I know exactly where it goes and how I'm going to add it in there. This is example 38.2 in the large inheritance tree chapter of the software design textbook.